My name is Peter. I work at SoundCloud on search and discovery and exploration features like this. And I'm going to talk a bit today about the Go programming language and how we use it in SoundCloud. So I think this is like the gaming and social media track, but it's going to be a bit of a mix, I guess, with the programming language track as well. But before I talk about any of that, I want to kind of take a step back and talk about software engineering. So I'm curious, does anybody here consider themselves like a software engineer first and foremost? A little bit, maybe. I certainly do. So forgive me, I'm going to start with the definition to lend my talk the illusion of credibility. If we can get it going. Aha. So software engineering, according to the ACM, is concerned with developing and maintaining software systems that behave reliably and efficiently, are affordable to this is super boring. All I care about are these first two words here, developing and maintaining. This is how I view software engineering personally, not as like a goal or as a thing that you can maximize, but rather as a process. So software engineering as a process, you're always starting with something, maybe nothing. You're getting some specs or some requirements, and you're building something, whether it's the initial version or version 2 or version 3. I look at the system as it exists today and compare it against how it should exist in the future. And not only this process for software engineering, but also kind of internally, this is how I judge myself, how I measure myself. The better I am at what I do, the more frictionless I can make this process. At SoundCloud, at least, this is how almost all of our features go, almost all of our development goes. We have somebody who's in charge of something, and they say, wouldn't it be cool if? It always starts this way. And my job is to say, yes, it would, and I'll do that for you. And then I go back to my desk, and I think, okay, what did I just get myself into? So when I'm thinking in these terms and I'm going from 0 to implementation or version 1 to version 2, of course I use tools. And so that brings us to Go. Why am I talking about Go? It's been my experience that Go is a really excellent tool for the process of software engineering. In my experience, it provides a small set of carefully considered primitives that are orthogonal to each other and can be easily combined to develop solutions to a large class of problems. Those solutions tend to be decomposable, testable, and maintainable. And I hope to do a bit of advocacy here and maybe convince some of you of this. But in order to do that, in order to show you some examples, we have to get a baseline understanding of the language. So just quick show of hands, has anyone heard of Go? Anybody? Yeah? Keep your hands up if you've programmed any Go at all. And something significant? Okay. All right. So we're going to do a quick run through of the language, just enough information to be able to understand the examples. So facts about Go. This is just so you can put it in your language matrix so you understand where it sits with relation to other languages. Go is statically typed, compiled, fast compiles, we'll see that. Produces native binaries on Linux, Mac, Windows, and a bunch of architectures. It's garbage collected. It looks a bit like C. It's got a big standard library, and it's got, among other things, baked-in concurrency, which is my favorite feature. Okay, so let's go right to syntax. Here's a pretty simple Go program. First line, package main. Every source file is a member of a package. Binaries are package main. Libraries are package something else. We have an import statements, just like in any dynamic language, I guess. And then a main function, it's the entry point of the program. Here we're defining two string variables. This first one is explicitly typed, in that we say var s1 is a string, and it has a value of this Icelandic name that I won't try to pronounce. And then this is exactly the same thing. It's still statically typed, but it's implicitly statically typed. So s2 is getting the type from the string literal. It's also a string. So the last line is a print statement just like C, and we run this, and in the background we've taken this text, compiled it, run it, and then forwarded the response back to the web browser here, and we get what we expect. Okay, cool. Simple syntax. A couple features really quick. Types. So in Go, the word type is a keyword. Use it to define new types. So here's a structure. It's a thing. It's got a name, which is a string, and a value, which is an int. Notice the declaration is reversed. I think that has a special name. Maybe it doesn't. Similarly to defining new structure types, you can create what's called a type alias. So Celsius and Fahrenheit are both aliases of float 32. That means they're kind of built on top of float 32s, but they are not float 32s. So you can construct them in this way. You can say this is a Celsius value, this is a Fahrenheit value, but you can't compare them. If you try to compare them, you'll get a compiler error because the types are mismatched. If you want to do this, you can cast them like this. And then this should work. Yeah. OK. So that's types. Hand in hand with types is interfaces. Interfaces are like abstract classes in other languages. For example, if we had a type runner interface, that is a collection of behaviors, in this case only one behavior, and it says if you have anything that has a function that takes an integer and returns an error, and it's called run, then by definition that thing is a runner, and you can use it in place of a runner in your program. So a concrete type would implement this interface. If we have something like a runbot 9000 with some stuff in it, we can define a run function on it, taking a distance int, returning an error. And of course, runbot 9000 cannot possibly fail, so it just returns a nil error. And now the runbot 9000 is a runner and can be used as a runner. Crucial point, there's no explicit declaration of intent. You never have to say implement a runner or anything like this. It just is. And the compiler builds this kind of tree during its compile. OK. So interfaces are first-class objects. You pass them around. Many standard library functions operate exclusively on interfaces. So for example, we can build such a function here, race, takes a distance, and then basically an array of runners that's variadic type syntax. So we just range over the runners. It's like a for loop. For each one, we're going to call the run method. If the error is nil, if the run succeeded, then hooray, it finished. Otherwise, they didn't finish, and then we print out y, print out the error. And then here's our main function. We run a race of 50 meters, I guess, between a developer with a certain clumsiness index, a little baby, and our run bot. And we see what happens. The developer finished, hooray, babies don't run, obviously, and the run bot finished, of course. If we run this a few more times, maybe the developer will trip over his shoelaces eventually. Yeah, OK. So that's the basic idea. Interfaces define behavior, types implement that behavior. OK, now to my favorite feature of the language is Go routines. This is how Go handles concurrency. They're essentially coroutines from communicating sequential processes. They're very lightweight threads. They're multiplexed onto one or more operating system threads. They're very cheap. You can launch any function, call in a new Go routine with the Go keyword, so it begins executing concurrently in the background. Note it's not necessarily in parallel. You don't get handles or any explicit Go routine management because communication between Go routines is idiomatically accomplished with channels, which are types, synchronized, and optionally buffered pipes for data. You can think of a channel as basically an Unix pipe, except with a type attached to it. Channels are first-class objects. You can pass them around like anything else. And you can have a channel of channels and thereby get like a lambda calculus or whatever you want. OK, so how do these work in conjunction? Let's take the kind of canonical example. You have a producer and a consumer. So here's our main function. We're going to make a channel of integers. Make is like an allocation primitive. It does some allocation and initialization for some types. We're going to go a produce function and then synchronously call the consume function. Produce takes a channel of integers. It puts 1, 2, 3 onto it. That's what this little syntax is. It's like put this value onto the channel. And then it closes the channel, which is like a signal to all the consumers. You're done. You can stop listening. And the consumer uses a range over the channel. Range is a special thing when it receives a channel. It's going to yield every value that comes onto the channel until the channel's closed, and then the loop exits, basically. So we yield all the values and just print them. So when I run this, I hope you just see 1, 2, 3. Yeah, OK, obviously, duh. Any takers? What happens if I do that? Any guesses? Does the output change?
They hang because you don't have anything next to you.
OK, let's see. Run. No output. Consistently no output.
Because you didn't wait for the consume to finish.
Aha. So exactly. We got this main thread of execution. We create the channel. Great. We launch a Go routine to produce. Great. We launch a Go routine to consume, great. And then we ran out of main. And when you run out of main, the runtime environment shuts down. And in this case, it shut down before allocating any CPU time to either of the Go routines we just launched. So they get shut down immediately as well. If we want to fix this, we can do one of these. And in order to do that, we need to do this. Okay. And now if I do it, 1, 2, 3, okay. So this is how you can conceptualize Go routines and channels. That's basically all we need to understand the examples, types and interfaces, Go routines and channels. It's like peanut butter and jelly. Or I guess here it would be like beans and toast or something. Okay, so back to this idea of process. Software engineering is process. I don't know about you, but when I get these specs from my product owner or whatever, I go back to my desk and I look at it and I say, I'm in over my head probably. What should I do? First, I'm going to build the simplest possible correct solution to the problem. So you don't have to buttress it with caveats. It doesn't work on this day. It doesn't work in this use case. So I build the simplest possible thing, try it out, and then iterate. Right? So make it better, make it faster, make it smarter, make it do better things. So keep this idea in mind, and I'm going to show you this first example where we're going to do kind of like a scatter gather. So you're going to collect data from multiple backends, aggregate it into a single response object, and then propagate that up to your requester. Think about how you might do this in your own language of choice. I don't know what that might be. Okay. I must say I've actually taken this example from another really great talk by a guy called Samir at Google. Afterwards, you'll see the link to the slides. If you're at all intrigued by this, check this talk out. It's really good. Okay, so we need to model a concept of a backend, which is something that can take a query and kind of return results. So we can model that in Go as an interface. A backend is anything which has a query method that takes a query string and returns a string. Think of it as like search results or something like this. So that's the behavior we want. We then define a couple of concrete types which implement this behavior. Like let's say we have a my backend, which is only a string, type alias. We define a method on that, which sleeps up to 100 milliseconds, and then returns a string, which is just the name of the backend / the query you gave it. So you can imagine this is like the results, and this is somehow work. Similarly, SoundCloud is somehow always full of Skrillex. So let's say we have a Skrillex. He's an empty struct that also has a query method. He's going to do the same thing, and he's just always going to say wub, wub, wub. Okay, straightforward. So what's the most naive possible way to have a set of these guys, send a query to them all, collect the results, and return it? Well, I guess you just do a for loop, right? And you just do it synchronously. So let's build that function. Query all takes one query, multiple backends, and returns basically an array of responses. So how do we do this? We build the array, we do a for loop over the backends, we run the query, append the results, and then return the group. Super simple, super dumb, super slow. I'd probably get fired if I did this all the time, but whatever, version 1. So in the main function, define 3 backends, server 1, server 2, and somehow a Skrillex. Record the time we start, send the query out, print the results, and record how long it took. So if you can imagine, every backend is going to take up to 100 milliseconds. They're going to take on average 50. 3 backends average 150 milliseconds. Let's see. 177, 239, 85, not too bad. So key points here. It's always in order, server 1, server 2, then Skrillex. And it can be as bad as 300 milliseconds, I guess. Okay, so there's iteration 1, and it's correct, and it works. But it's slow. So what's iteration 2? What's the simplest possible way to make this faster? You actually maybe do the scatter gather. Even my product manager can understand that you don't need to wait for all of them in sequence. You can just wait for the longest one, and that should be enough time. So think about how you would go from this naive version to like what I've just described in your own language of choice. Probably you need some kind of framework. Probably in Ruby you're doing an event machine thing. In Go it's really simple, so let me do that. Let's fire the queries concurrently. We're going to have the same query all method, the same method definition, but we're going to do things differently inside. We're going to have this scatter phase, the query phase, and the way we're going to model this is by building a channel of strings, a channel of results, with a buffer depth exactly equal to the number of backends that we're going to fire against. Then for all of those backends, we're going to go a closure, an anonymous function that calls the query and then puts the result into the channel. So there's the scatter phase. And then the gather phase is almost identical. We build this array of results. For every backend that we fired a go routine for, we're going to drain the channel. So here we're draining a value from the channel and appending it directly into the result slice. And then we return that just like we did before. So note that the method definition didn't change, and you'll see the way we call it isn't going to change. All we did was change the implementation. This is what an interface kind of gives to you. So I'm going to run this. And I think if I did everything right, this should never exceed 100 milliseconds, right? Because that's the longest one can possibly take. And it should often be quite low. I think it should probably average around 50. So this is cool. We've made like a really significant improvement. What we can do even better still, we're kind of at the limit, the theoretical limit of how fast this can be given the current constraints. But we can even go a step further and say, if we need it to be faster, if we need to bring the long tail of these query times in, we can replicate the backends. And so we can have the same backend with the same content replicated, let's say, across data centers, and then fire the query to all of these replicas, or maybe some intelligently derived set of replicas, and then take the first response that comes back and use that, and therefore bring the long tail of query times in. Think about how you did that in your language. You'd have to figure out some way to handle all the failure modes. You'd have to probably clean up all these bad values somehow. A lot of synchronization, I think, no matter how you cut it. But in Go, we can lean on these primitives. We can lean on the fact that the channel is synchronized and that Go routines are very lightweight. So what we can do is build this type called replicas. Replicas is an array of backends. In theory, they should all have the same content. And then on this new type we've defined, we can implement this query method that satisfies the queryable interface we defined. And what it's going to do, it has, again, the same interface, takes a string, returns a string. Internally, it's going to do just like the query all method does. We're going to build a channel. We're going to feed query results into it. But instead of aggregating them, we're just going to return the first one that we're able to drain from the channel. So what happens here? We're launching all these Go routines. One of them is going to win. It's going to push the first value in. We're going to return that immediately. But all the other Go routines are still running. They're all still doing their work. They're pushing their values into the channel and then exiting. Once the last one's done, all the handles on the C channel are going to be released. And then the C channel is going to get garbage collected. And this is fine. This is fine. We're burning some CPU time on these replicas, but that's OK. We decided it was worth the cost to bring the long tail in. So then to query replicas, we have to build the replica set. So you can imagine replicas, my backend, we have foo1, foo2, foo3. We have another set of replicas for bar 1, bar 2, bar 3, bar 4, bar 5, you can imagine. And then frighteningly, we have 5 Skrillexes all in a row. And we can see the rest of the function is exactly the same, query all. We didn't change that method at all because the replica set is still a queryable thing. So we run this, and hopefully, on average, these are pretty much faster too. Yep. There's a 70. OK. Doing good. 3 iterations, 5 minutes. My product manager is pretty happy. Think about how you would have to do this in your own language and how maybe how much time you would need to allocate to go through these iterations. One thing I really love about Go is that the primitives compose so well that you don't need to spend a lot of time building an infrastructure. You can just, or using abstractions or things like this, you can go directly to the core primitives and get exactly the behavior you want. It's pretty cool. OK. So this is like one small-ish problem. But you can imagine, and at least for me, this happens all the time, I'm tasked with building features that are composed of many of these smallish problems. Oftentimes, the behavior that's required can be described very easily in a very straightforward way. It might be, get a piece of data from this API, enrich it via this database, transform it in this way by these set of business rules that I'm going to give to you, and then store the result in either this database or this data store, depending on blah, blah, blah. a lot of feature requests break down, for me at least, into this sort of prescriptive set of rules. And I view it as sort of my task as a software engineer to transform this in as good and frictionless way as possible to a working implementation. So for me, a lot of things break down into this pattern, this idea of pipeline data processing. You're given something, you do work X, Y, Z, and then you finish somewhere else. And I guess the canonical example of this would be like an extract, transform, load sort of workflow. So in this example, we'll be subscribing to like an event publisher. It's considered just a stream of messages somehow. We'll convert the messages to enrich data models, so we'll like pack some other stuff in there, and then we'll feed them into a data store. This comes up kind of a lot for me, maybe for you too, I don't know. So how do we model this? Let's treat each of these distinct stages as a function. So let's start at the listen function. Here our listen function simulates an infinite stream of messages, pushing them down an output channel. So we have this func listen, which we have to pass a channel of message, whatever that is. And we do an infinite loop. We wait up to 250 milliseconds. And then 60% of the time we're going to write foo, 40% of the time we write bar. Continue. Okay, straightforward. So let's now have an enrich stage, which is going to read a single message from an input channel, process it, and then push the result down the output channel. So takes two channels, enters another infinite loop, read the message in, put some nice little stars around it. You can imagine this is actually doing work, let's say. And then push the enriched message now out the output channel. And I mean, that's literally it. This is production grade code with no explicit synchronization, no condition variables, no timed waits. Everything falls out of this go-routine channel model. It's already synchronized for you. And as we'll see, it's already super scalable. Okay, last stage is storage, so ETL load. We'll model this as a function too. We'll take only an input channel because there's nowhere else to go afterwards. Another infinite loop, we receive every message off the channel, and then we're going to just store it to the screen, I guess. You can imagine this is going to a MySQL database or something. Okay, so these are our stages. Now we just have to wire them together. So in our main function, we're going to build an infrastructure of channels, of pipes, one between the listener and the enricher, so to the enricher, and one between the enricher and the store, so to the store. And then we launch the actors. We launch the things doing the work on these channels. And then we'll wait a second and see what happens. So I hope you'll see it works as expected. Yeah, sure. Run it again. Maybe it's slightly different. Right? Cool. All right. So what have we done here? We've modeled this very simple business domain set of rules in a very simple implementation that maps directly to what you kind of perceive the necessary work needs to be. And for me, this is so important. I don't like to spend my brain cycles thinking in terms of like the 40 layers of abstraction I had to use because my language doesn't natively support concurrency. You know, I like to think about the business rules that I need to implement and making the path from an idea in my product manager's head, an idea in my customer's head, to reality like as frictionless as possible and as quick as possible. Using channels to pass ownership of a message between stages in this way makes this program naturally concurrent. It also cleanly, I think, separates the business logic from the transport semantics. So you have a total separation of concerns, not only across business rules, but also across implementation schemas. Note that because the channels are unbuffered, you get automatic back pressure, which in my experience is what you want. That means you won't ever take on more work than you can actually handle based on your external resources. So in my experience, it's better to push that failure mode out and not accept more than you can resolve. So that's cool. That's what you get automatically. So implementation 1, great. I roll it out, and suddenly, let's say my CTO says, oh, this is great, but what are all these bars doing here? I didn't expect to see any bars. I don't want to see any bars. So okay, how would we solve this normally? Maybe we would put like a little if bar, then do something weird in the listen stage. Yeah, maybe. But let's stick with this model and let's have a filter stage. So A filter, again, takes an input-output channel, reads a message. If the message is a bar, then drop it. So this is the direct translation of a business rule to a stage. And we can just plug it in to our infrastructure, and we don't lose performance for this, as we'll see. It maps directly to the concept of what we're directly trying to build without any abstraction. And of course, it's safe and easy to abort a pipeline if you think about the model of actors doing work and pipes used to transport the work. So we can just drop this message on the floor if we need to. And it's really safe and no problem. So to wire it up, we just add a new channel. And we add a new actor. And I hope we won't see any bars. Sure. Cool. Easy. There's no complex abstraction to get lost in. You can look at this function, read it from top to bottom, and understand immediately what it does and how it works. In Go, the code does what it says on the page, and I find this super, super valuable. Similarly, scaling the actors for a stage increases the concurrency of the program. So if our enrichment stage wasn't just sticking two strings on the end of a string, if it was actually doing work, maybe that would become the bottleneck in this. And one way to solve that bottleneck problem is to have concurrent, let's say, lookup actors running at once. Imagine doing this with your language of choice. How would you have to do this? You would have to synchronize somehow the handoff of a message to an actor, and then synchronize putting that back into a shared pipeline to the filter stage or something like this, or sorry, to the store stage. You'd have to maybe build a thread pool or multiplex jobs onto workers and then demultiplex back in, blah, blah, blah. But if you use these Go primitives, literally all you have to do is spawn more Go routines doing the work you want. Reading from the same channel because they're synchronized, and writing to the same channel because it's synchronized. And you can, in this way, get increased concurrency on very specific points. Channel operations are a synchronization point across Go routines, so multiple Go routines can safely read from or write to the same channel. Each message will go to exactly one receiver. So I'm going to hit run, but you're not going to really notice a difference because we just are sticking strings on there. But you get the point, I hope. Okay, so that's cool. But now let's do another conceptual change here. Let's say, what if so the source of our data isn't a message queue? What if we want to change kind of the paradigm of the service and say it's an HTTP server, and that every message is not an event, but an HTTP request? We can do this. We can change our message type to hold the relevant information. Let's say we have a piece of data that comes and extracted from the form values. And then what we also need is a signal channel to signal our HTTP request handler that we're done with the pipeline processing. But if we do this, if we redefine the message structure, we can modify the pipeline to work on HTTP requests. So we have to change the listen. The listener should now start an HTTP server rather than generate messages. That's relatively easy to do. We define this handler function, H, which takes a response writer. That's where we're going to write output to, and then the request that comes in. In the handler function, we build this message from the form value, and then we allocate a signal channel. And then we push that message into the pipeline. Then we're going to block here, and we'll wait for a done signal. If we didn't have a success, then we're going to write aborted in the data. Otherwise, we're going to write OK. So that's the handler. We need to wire the handler up to a route, incoming. And then in the listen function, we're going to block forever on this listen and serve. So this is the HTTP server. OK, that's all we need to do there. But we need to do one other thing. Whenever our pipeline completes, whether it's an abort or a success, we need to signal the handler to write a response to the client and shut down the connection. So in our filter stage, if we drop bar on the floor, then we need to tell the done channel that we had a failure. In the store stage, if it got all the way there, we had a success, so we signal success. Okay? Otherwise, everything is identical. We're passing around pointers to messages rather than messages, because in theory, you would change the content of this context. It would maybe be a lot bigger. But I'm going to run this now. Rather than sleeping for a second, we're blocking forever. Then I hope, okay, 8080, Incoming data foo. Cool. Foo. Foo 2. Foo 3. The dreaded bar, not there. Aborted. Cool. Bar 2. Feature request. Yeah, so the cool thing here is we didn't change anything because conceptually you don't need to change anything. The way that you can describe what this program does, whether it's this events are coming from an HTTP server or coming from a message bus, like it doesn't change the business rules. And indeed, we haven't changed our business rules. We just changed the functional component that's different. This is really cool. And for me, this is an amazing like enabling capability. So, in recap, for me, Go helps the process of software engineering to be a lot more pleasant. It gives you simple orthogonal primitives that combine well. It makes code readable and maintainable. And as a result of all this, they say that Go code is code that grows with grace, and I tend to agree. So I hope I've given you a taste of that. That's it. Thanks a lot.
Questions, anybody? We're a little bit ahead of time, so feel free to ask more than you thought.
Right, so in terms of all like core routines, it looks fairly similar to the akka in Scala, so the akka framework, an actors framework in Scala. Is the actual, well, okay,
Yeah.
with some changes which I don't know of, but with the terms of the redirection to the channel, is that a language construct or is it some sort of a function? I mean, the question is, can you define the functions like that, acting similar way with a similar sort of, is there in like a restrictive characters or is it a language construct or what? Like,
I'm not totally sure what you're asking.
okay, so for example, in Scala, you can define any function name. Is this similar for Go?
You can define any function name?
Yeah, for example, redirect, what you had in redirect in stream, redirect to the channel, is a it's a function with like funny name. I was just wondering if that's the language construct. In Go, it's redirection to a
Oh, the arrow.
Is there a
Oh,
language construct?
do you get operator overloading? You mean things like this?
Yeah.
No, there's explicitly no operator overloading.
Is an operator? Okay.
Yeah. Does that answer the question?
Yeah, that's my question.
Okay. I could expand on that a bit and say that's actually by design. The Go calculus, that they've landed on the idea that operator overloading hurts you more than it helps you. So this is part of the Go philosophy.
So what about debugging this? I mean, concurrency is always nice, and this looks really impressive, but what if it goes wrong? What kind of tool sets do we have to find out what went wrong?
What if it goes wrong? Okay. Let's see if I can do... Oh, maybe not. Okay, so debugging in general, there's GDB support, so you can load up a Go program in GDB. But that's often not like the thing you really care about with concurrency. So let's go back to this producer-consumer thing. Yeah, here we are. And so what's like the most common thing when you have a concurrent program? Like the most common bug would be what? Deadlock, probably, right? A common bug. So how can we induce deadlock here? If I produce C and then consume C without launching one in the background, then this guy is going to try to execute, but he's never going to be able to push this value because there's never going to be a receiver, right? So in theory, this would block forever if I ran this as it exists here. So let's see what happens. Oh, well, yeah, that happens, first of all. Can I try that? So the Go runtime gives you deadlock detection. And when it detects this, it gives you kind of a stack dump, which maybe you can't see so well in this tiny little window. But if this were a real file, you would see exactly where each Go routine, this is like the runtime environment, but we only have one Go routine, and here it is, main.main, line 10. I'm sorry, I don't have line numbers, but 1, 2, 3, 4. Okay, maybe it doesn't translate. But in general, you get, in the runtime, it's kind of sophisticated enough to give you detection of a large class of synchronization problems. So this is cool. But even like taking a step back, if you model your problem in terms of like Go routines and channels, a lot of the things you normally have to care about, you'd simply no longer have to care about. Taking a key from some earlier talks in the bigger room, You certainly only very rarely have to do locking at all, because the channels are synchronized. Sometimes you use a wait group, but I mean that's really the extent of the primitives that you dive into. So I've been programming Go professionally for a year and kind of casually for, well, since it was introduced 3 years ago. And I cannot say I've ever used a debugger. And I've done some pretty big stuff. So that's cool too in a way, in my opinion.
Are you working in a large team or by yourself?
I work in a team of about 4 or 5. But at SoundCloud we have very fluid teams, and this changes a lot, bigger and smaller. And Go is a prevalent language, but we also do Scala, we also do Java, a few other things. But we're kind of like a service, we're trying to be a service-oriented architecture sort of company. And in my experience, Go is like the perfect language for this type of service. So I'm trying to convince other people of that as well in the company.
What IDE supports that Go?
There are several, including several that have been built kind of from the ground up. But for my money, the best you can do is Sublime Text 2 with a CodeIntel type plugin called Go Sublime. Maybe I can just show you. It's really cool. I'll try not to load up any terribly production grade code. Dangers of a live demo. Okay, so blah, blah, blah. But you get this really nice completion, and then you get drop down, and then you get this, and blah, and you get build support, undefined key. Okay, yeah. Oops. Build, no errors, automatically runs a test, tests okay, blah, blah, blah. Pretty cool. And the Go language is lightweight enough that like this is possible, and it like doesn't require a ton of storing parse state or anything in the IDE.
Two questions. The first one is about the concurrency model. Go is using CSP and Rendezvous for channel. I mean, it's a real CSP or a modified one?
It's certainly inspired by the CSP model, but I can't say like, is there a CSP spec that you can either abide by or fail at? Like, I'm not sure about this actually.
There is one, but it's about guard and stuff like that.
Okay, so I would say it is not a strict proper CSP implementation, it's more like inspiration.
And you didn't miss the asynchronous channel and type of the actual model, or?
You approach it with the concept of buffered channels, but let's see how to answer this. I wouldn't say that I miss it because Go is kind of first and foremost a productive rather than a theoretical language. And in that context, in the context of like pragmatism, asynchronous channels, like they enable this huge class of really interesting models that you can build. But when that model like interfaces with silicon and memory and stuff and resources, you need to care about things that you didn't need to care about at the model level. And so asynchronous channels are like, to support them properly, I'm kind of speculating here, would require an enormous increase in the complexity of the language. And Go generally, when faced with a decision in these terms, will go with the simpler solution, even if it means leaving features out. So I'm not sure this is why there are no asynchronous channels, but I can tell you this is why there is no generics in Go yet. A number of other things, no exceptions as well.
Thank you.
Partially, perhaps already by the previous question, but how are the Go routines and the channels implemented? Is there anything we need to worry about in the implementation, like bottlenecks or?
So when you spawn a new Go routine, it takes up like 4 kilobytes of memory. So that's your overhead. You can get to about 50, 100,000 in a program without a sweat. Some of them, if you do it intelligently, you can do about 1 million. So it's no problem to do like n Go routines per request, for example. This is not a problem. I'm unfortunately not super familiar with how channels are implemented, But if you had concrete questions you're concerned about, I could maybe answer those. Okay.
Later. Thank you.
Yep.
Excellent, thank you.
Cool.
As I say, if you could just rate the session on your way out, it's greatly appreciated, and thank you very much for your time.
Thank you all.